Okay, good afternoon, grade 9s. I'm going to start with the consolidation this afternoon, and as I said, I'm going to start looking at factorization, and this is part of consolidation for algebra in grade 9. So in terms of factorization, remember in class we have studied factorization of polynomials by using different methods. The basic method is by extracting a common factor, and then from there we go on to calculating or factorizing also binomials in the case of a difference of two squares, and trinomials in the case of the trinomials in this case. So I'm going to start first by going back a little bit and doing a little bit of exercises or questions on how to expand and simplify. This is the opposite process to factorization, which is where I'm going to get at to. So in this case, what we need to do is we need to follow the laws of exponents, etc. You know that from these multiplication is where I actually come out then later to reverse and go on to factorization. So I'm going to start by looking at some exercise. These one actually are from your revision exercise book. This is particularly, this is taken from the exercise book on the Man Action Series. Grade 9 edition, and I'm going to look at some exercises where we need to simplify. So I'm going to look at some simple exercises. So for example, when we need to factorize or expand things like, so we have, let's just put it here, so expand and simplify. Okay, so I'm going to take number 1 here, and that would be, say, minus 4x times 6x minus 3y, and then I'm going to look at I'm going to do another example here, and that will be a little bit more complex. So now we're going to have something like 3p minus 5 times 2p minus 1, and then so that will be b. And then we're going to look at a couple of other examples. So let me just start from here, from this viewpoint. Now remember that when you multiply, you're using the laws of exponents. So you multiply coefficient by coefficient, and then you look at the variables in order to find the multiplication. So in this case, I'm multiplying this monomial or this term by every term inside the polynomial that is inside the brackets. So I'm going to proceed, and I'm going to go and say, in this case, when I multiply minus 4x times x, that would give me that's minus 24, minus 4 times 6, and then x times x, that would give me x squared. Now when I repeat that multiplication now of the same term, remember you got to multiply by every term inside the bracket, then you also will have then plus, because minus 4 times minus 3, that's positive 12, and then x times y, because I like variables in this case, I'm going to say x and y. There's no ways to simplify that any further. Now I look at the expression as a whole, and I see if I've got like terms that I could simplify. Like terms means that you have the same algebraic side, the same variables, and those variables also include the exponents. So it's just not the one is just the exponents that you look at the variables and the exponents, and if they are the same, then you can go on and simplify them further. So that expression, since it doesn't have any further factor or any further simplification, I will leave it then as my final answer. Okay, now in the case of binomials, when you have two binomials that you're multiplying together, the multiplication happens very similarly. The only difference here is that I'm going to have to multiply every term that is in the first polynomial, or in the first binomial in this case, multiply by every term inside the other one, or the second polynomial in this case. So let me just start here and say, well, what I'm going to do is I'm going to start multiplying here the first term. So the first term in this binomial, first term in this binomial multiply by the first term in that binomial, and again that first term multiply by the second term in the other polynomial. Once I've done that, then I come back and I now take this term, multiply it here, and that term, and multiply it there. Now remember that there is a difference here, and that is that you could actually go and do these products by inspection, but I think that will be a little later when you master the the actual skill. So for the time being, I would prefer to actually go step by step and make sure that we have everything of the basics that we need. So when I do the multiplication here, I'm going to start and I'm going to say, so I need to multiply 3p first by 2p. And remember, you multiply coefficient by coefficient, so 3 times 2 is 6. And then p times p, because they both have exponent of 1, and 1 plus 1 is 2, so that would be 6p squared. Then I multiply the 3p by the second, which is minus 1, so 3 times minus 1 is minus 3, and then p, because the variable you cannot leave it behind. Then I'm going to now finish with this, and I'm going to go to the next term, so minus 5. I'm going to then multiply minus 5 times 2p, so minus 5 times 2, that's minus 10p, and then multiply minus 5 times minus 1, and that will give me positive 5. Once I've done that, I have basically removed the brackets by means of multiplication or using distributive law. I've got that, then I can just go and say, let me look at my expression and see if I can simplify further, in this case by removing or by simplifying any like terms. Do I have any like terms? Let's have a look. I've got a term here that has a p squared as an algebraic side or variable side. There isn't any other p squared. Yes, I do have variables or terms that contain the variable p, but none other that has this p squared. So that means that this first term is going to stay as is, so 6p squared. Then I'm going to take and I'm going to look and I say, do I have other terms that contain the variable just p as it is in this case? Yes, there is. You have minus 3p and minus 10p, so we say that those two are like terms, and because they are like terms, I can just go on and say I can add the coefficients, so minus 3 minus 10, that is minus 13, and obviously you keep the variable because remember that you were adding like terms, so they have to be of the same likeness as they were before, so they have to have the variable p. The same thing here, the only number or the only independent or constant term that I have in this expression is 5, therefore it has no other term like with it, so plus 5 will stay as is. Okay, so one more example in expansion. In this case, what I'm going to do is I'm going to look at something a little bit more complex. So let's say I've got two, and this will be the last example. I'm going to look at the product of, I've got 5 times 2y minus 1 times 3y plus 2 minus 4y minus 5, all of that to the power of 2. Okay, so when I look at this, I'm going to then start first by looking at multiplication, and again I've got a 5 times and bracket times another bracket. You need to realize that multiplication always happens term by term. One common mistake here is that many pupils actually tend to multiply the 5 by every single term using the distributive division. You don't realize that, or they don't realize that this is a product of 3 terms. And when you multiply, and I'm just going to, apologies that I'm going to use numbers, but when you say 5 times 3 times 2, you don't say 5 times 3 and then 5 times 2 and add them together. You simply say 5 times 3 and then you take that answer and you multiply it by 2. Or you multiply 3 and 2 and then you multiply the answer by 5, which is what I'm going to do in this particular question over here. Because I've got two binomials and I already know how to multiply binomials, what I'm going to do is I'm going to take the two binomials and multiply them together, and once I've done that, I'm going to multiply the answer by 5. Okay, so in this case, I'm going to go on and say equals, and this will be 5 times, and I'm going to open the brackets because remember that I haven't multiplied by 5 yet. I'm going to solve the product of the two binomials and then multiply that answer by 5. So I should actually have the 5 independent from everything. So in this case, I'm going to multiply, and I'm going to say 2y times 3y. Remember that I'm going to multiply the first term of the first polynomial by all the terms of the second polynomial, and then I'm going to multiply all of them by -1. So let's go. So 2y times 3y, that would be 6y squared. Then 2y times 2, that would be plus 4y. Then minus 1 times 3y, that's minus 3y. And then minus 1 times positive 2, that is -2. Okay, I haven't multiplied by the 5 yet. Before I do that, I just want to go and talk about the second term. So in this case, what I have is that expression minus the square of 4y minus 5. remember the laws of exponents that say that your exponent dictates how many times the base has to multiply together. So one easy way of doing this, if you cannot do this product by inspection, will actually be to write. Now remember that the minus in the front here is important because that minus is affecting whatever comes out of these, the square of these binomials. So I can treat that as me saying this is 4y minus 5 times 4y minus 5, because remember that the exponent, the value of the exponent, dictates the number of times that you have to multiply the base. So with that said, I'm going to go on and say, now I'm going to go to my next step, and I'm going to say, so here I've got this, I'm going to multiply by the 5, so 5 times 6y squared. I could have simplified my expression here. Let's just start from there. I could have simplified my expression here, but I'm not going to do it yet because I will be able to simplify the whole expression later once I've opened all the brackets. So I'm going to then start here and say, so 5 times 6y squared, that is 30y squared. You only multiply the coefficients because there's no variables here. And then you multiply 5 times 4y, and that will give you plus 20y. And then 5 times 3y, and that is minus 15y. 5 times minus 3 is minus 15. And 5 times minus 2, that is minus 10. Minus, and then remember that this minus basically affects everything that comes out of there. So I'm going to still open a bracket, and I'm going to then multiply in here. So remember, you could do this product by inspection. I'm just assuming that you're struggling with doing the product by inspection, and I'm going to do it like if you did not know how to do it by inspection. So I'm going to multiply 4y times 4y, so that is 16y squared. Then multiply 4y times minus 5, and that is minus 20y. And I'm going to then multiply minus 5 times 4y, and that is going to give me again minus 20y. And then I'm going to multiply the minus 5 times minus 5, and that's going to give me plus 25. And this is the product of the two binomials. Now remember that that product is affected by this minus in front. So before I proceed to try and simplify all the like terms, what I would like to do is I would like to remove this bracket by changing the sign of every term inside the bracket. Literally what it means is that you're multiplying by -1, which is meant to be the coefficient in front here. Okay, so I'm going to say, so this is 30y squared. Again, I could have simplified a little bit, but I'm not going to do it yet. Plus 20y minus 15y minus 10, and then I'm going to say, so this is minus 16y squared plus 20y. So remember, the minus becomes a plus another 20y, okay, minus 25. And as you can see now, I've got an expression literally that is clean. The only problem is that that expression isn't simplified. So that's what I'm going to do next. I'm going to proceed to simplify this expression. And for that, what I'm going to do is I'm going to look for like terms. So let me just try and use a little bit of color here. So let me start with a quadratic term. So I've got 30y squared here, and I've got minus 16y squared there. Okay, so I could just say that would then give me 30 minus 16, that is 14y squared, and I've simplified those terms. Then I'm going to go to the next one, and I said, okay, so let me just see how many terms do I have that contain a y. So I've got, let me just move this up a little bit. Okay, so then I've got plus 20y minus 15y plus another 20y plus another 20y. So all of those terms are like terms because they all have the same literal part. They all have the same variable. So I'm going to then simplify those, and remember, when you simplify them, your coefficient will change, but your value here will stay the same because they are all of the same likeness. So I've got 20 minus 15, that is 5 plus 20, that is 25, and 25 plus 20, that is 45. So that would be plus 45y. Okay, and that is the simplification of all of those. What else do I have apart from that? Well, I also have a minus 10 over here, and I've got a minus 25 over here. So I do have another two constant or independent terms that I need to add, and minus 10 minus 25 is equals to minus 35. As you can see, this expression grew and grew and became very long, but now looking at like terms, look how simplified that expression is, and now there is no further simplification, so I will stop it there. Okay, now this is all there is to know with regards to expanding algebraically. Obviously, laws of exponents play a big role in this, so practicing the laws of exponents will allow you to be able to work these multiplications a little much more efficiently. Now, from there, we're going to move then to factorization. And remember that in class, we have looked at the factorization, and we've looked at the factorization looking at a diagram that looks something like this. So when you try to factorize, the first thing that you're going to tackle is you're going to look at your common factor. So you're going to see if your expression has a common factor. Yeah, I think I made that rectangle a little bit too small. Okay, but let's say I've got a common factor, so I've been able to extract that common factor to simplify the expression. Now, once I've done that, once I have extracted a common factor, what I'm going to do then is I'm going to look and see what my expression is. Is my expression a two-term polynomial? Okay, other words known as a binomial. Okay, or I'm going to look and say, is my expression a three-term polynomial? In other words, also known as a trinomial. And the last, which is not for an interest of study for now for us at the moment, is it a four-term polynomial? And we will see later on in the course how is it that we do this. So in this case, there's a different way. So I'm going to focus basically on these two. So when we have a two-term polynomial, we say that the only type of polynomial, only two type of two-term polynomial that can be factorized is if it is a difference of two squares. Okay, many teachers and pupils actually know it with the abbreviation DOTS. So difference of two squares. Okay, and the typical manifestation of a difference of square is that you have a term, let's call it A, and I'm just going to call it capital A for interest sake, squared, and then minus B squared. So in other words, you have a difference of two terms and each one of them are square. Now, I want to expand a little bit on the fact of the squares. That doesn't necessarily have to be variables. It could be numerical values. It could be a combination of both for as long as it is a perfect square. Now, in order to tackle this, one thing that I do recommend is that you practice a little bit of your numerical squares. So let's say, you know, practice your squares from 1 to 12, and then practice your to realize that a variable is perfect. Consider a perfect square if the exponent is an even number. Now, when you have a condition set to differentiate or to factorize by using difference of squares, you factorize the difference of squares basically by multiplying the sum and the difference of the square root of the two terms that you have as your difference of two squares. And we're going to see a couple of examples a little bit ahead in the consolidation session today. All right. Now, if it is not a difference of two squares, then what you're going to look at is the other possibility is if it's not a two-term, and if it's two-term and it's not a difference of two squares, then I don't have anything else to do. But if it's not a two-term, if it happens to be a three-term, how is it that we can factorize a three-term expression? Now, in this case, you factorize a three-term expression if it is a trinomial. And for the sake of the course that we're busy doing now, we're only going to focus in trinomials when they're written in the form x squared plus p times x plus q. So in other words, the coefficient of the square term is 1 for now, and then obviously these p and q are two numerical values which we will be able to work with a little later. So if that is the case, then how do we factorize a trinomial? We're going to do this by using a couple of examples. Okay, so the basic idea is I look first for a common factor. Always start first with your common factor. Take out your common factor, and after you've taken out your common factor, then check out, do you have a two-term expression, do you have a three-term expression, and then see how we can factorize further. If you don't have a common factor, still you need to look and see whether it's a two-term or a three-term, and see if it fulfills any of these two properties, whether it's a difference of two squares or whether it's a trinomial that can be factorized. And that is in essence exactly how this goes. Okay, so what I'm going to do now is I'm going to take some examples of factorizations. I'm going to pick examples from the textbook and see the various variation of these examples on how to factorize. So in this case, we're going to do some exercise, and the exercise or the order of the exercise say factorize fully. Okay, so what am I going to factorize fully? I'm going to have an expression like this, for example. We have, let's say we have minus 3 x minus 12. Then I'm going to have another expression that looks like this. So we have, let's say, x squared times a plus b plus 3 times a plus b. That's a different type. And then we're going to look at a factorization of a polynomial that looks something like this. So let's say we have x squared times x plus 4 plus 9 times minus 4 minus x. And let's see how we can factorize that. So let's just start from here, and then we can move on a little closer later. So let me just start from here. So remember that the first thing that I need to look at is when I factorize is I need to look and see if I do have a common factor. Okay, and remember, checking out for common factor is if you have a highest common factor between all the terms that you have in your expression. So in this case, I'm going to look here, and I said, well, let's just start with the numbers first, because I see that there's an independent term here. There is no variable, therefore I shouldn't be looking for a variable common factor. So how am I going to factorize this? Now in this case, I know that minus 3 is a factor of negative 12. So I could take out negative 3 as a common factor of that expression. Now, once you've identified and you've taken out your common factor, the next thing is you need to find out what is the remainder of my division when I take out that common factor. And remember, in this case, we're going to base ourselves going back to the previous exercise when we were doing the multiplication. Remember that eventually you want to arrive, so this is an expression that was already factorized, and what I did here was actually to multiply it in order to expand it. So what you're getting now is the expanded form, and what we're asking you to do is to go back to that form. Alright, so I'm going to then say here, and all I need to do once I've identified and taken out my common factor is I'm going to take every term of my polynomial and I'm going to divide it by that common factor. So in this case, when I divide minus 3x divided by minus 3, that's going to give me x, and then minus 12 divided by minus 3, that's going to give me plus 4. Now you can double check and see that if you were to multiply this expression again, you're going to get back to where you started from. Then you know that you have factorized the expression properly. Now in the next case like this, now when I see something like that, I'm very tempted first of all to try and expand it and then try to simplify it. But if you realize, you will see that in this case this is a single term because it's a multiplication, and one of the factors in that term is a plus b, and on the other side you also have a factor which is a plus b. So this factor a plus b is common to the two terms of this expression. So when I want to factorize that, I will then be able to say a plus b, because it is repeated in both of my terms. I will be taking I will taking that out as my common factor, and that will be a plus b is the common factor of x squared plus 3. Remember, when you divide that by x plus b, basically you're taking away the a plus b and you got left the x squared, and if you're taking the 3 times the x plus b, you're taking the a plus b away and you're left with the 3. Now you could check this one or two ways. You could multiply those two and expand it as a single expression, and then you do that the same there and you will realize that you got exactly the same values. I'm not going to go through that now because the point here was to learn how to factorize. So when I did that, then I realized that I could I factorize expression completely because I've converted it from something that was the sum of two terms to a product of two factors. Even though each one of those factors in themselves is a sum because it's a binomial, still it is a product. Before it was just a single term or a single polynomial with two terms. Now it has become a single term, and that's what the factorization basically means. Okay, all right. So let's go to the next one, and in this last one I've got a little bit of work to do before I can attempt to factorize, because as you can see I've got here this x plus 4, which is my sort of one of my factors. Okay, and why am I focusing on? Because when I look here by intuition I see that there's something similar there. What is the difference? The difference is that in this case I don't have x plus 4, but I've got the opposite of 4 and I've got the opposite of x. So how can I sort this problem out? It can be easily sorted out by saying, well, if I were to multiply that expression by -1, or multiply this by -1, I would have obtained what I've got inside the bracket. So -1 times x would have given you -x, and then -1 times 4 it would have given you -4. So you could almost say that these bracket here is actually the opposite of what is in there. So I could convert this bracket to look exactly like that by simply taking out a common factor. So by making a simple change of sign to that sign and change that into a negative, okay, I will be able then to remove the minus from the 4 and the minus from the x. Now, because they are both positive, I can then rearrange them and write them both in this way. And when I do that, you will see that now my expression has been turned into something that can be factorized because it has a common factor x. Let me just adjust the camera a little bit. It has a common factor x plus 4. Now, since that x plus 4 is a common factor, I could then pull out that common factor and say, so x plus 4 multiplied, and then inside the brackets here I've got x squared minus 9. Okay, now remember that we said that looking at factorization, so the moment you take out a common factor you need to look and say what I've got left. So in this case I had an x plus 4, which is just a binomial. It's not a difference of two squares because the term that links the two terms is actually positive. So the sign is positive, therefore it's not a difference of two squares. Same thing here. Once I factorized there, I realized that none of them were positive. However, now that I factorize here, there's a positive sign linking those two, but here there is a negative sign. So the interesting thing is I need to try and check out and say, well, is this possible, a possible difference of two squares? Could I factorize that as a difference of two squares? Well, let me have a look and see if it ticks all the boxes. Is it a difference? Yes, there is a minus connecting the two. Are there two terms? Yes, I've got a binomial here, so it's a difference of 2. Is that term a perfect square? Yes. How do I know that? Because my exponent is an even number. Is that term a perfect square? Yes, it is. Why? Because the square root of 9 is 3. So identifying that as a different squares means that I could factorize that further. So this is where, remember, I'm going to say this is the product. Well, how do you simplify or factorize the difference of two squares? It's the product of the sum and the difference of the square terms, or the square root of both the terms. So x plus 3 and x minus 3. Okay, and obviously because this x plus 4 has not been affected, we haven't done anything with it, we then carry it over, and then we have the expression that fully factorized as x plus 4 times x plus 3 times x minus 3. Now with time, if you want to check whether you've done it correctly or not, you could actually multiply those ones and go all the way back here. As a matter of fact, you should actually go all the way and multiply those two out and compare the two. Okay, so I'm not going to spend the time on this. Now, where do we use factorization? I'm going to do one or two more questions now where I need to factorize either difference of two squares or trinomials so that I can explain to you, or I can show you how to factorize them, and then we can just go and work out. So, alright, so let me just get there. So here we go. Now I'm going to remember, I'm still factorizing fully. In this case now I'm going to factorize something like this. I'm going to factorize 4x squared minus 64. Okay, and then I'm going to factorize minus 8x x squared plus 8, and then I'm going to simplify, or I'm going to factorize minus, or 3x squared, not minus 3, 3x squared minus 243 y squared. Okay, so I'm just focusing more now on the difference of two squares. So A, B, C. So remember, and always in the back of my mind, I need to just have a look and say, do I have a common factor? And that must be the first question that I ask myself. Do I have a common factor? Do I factorize by using a common factor? So when I look at this, I'm going to go on and say, well, let me look at that expression and see if I've got a common factor. Do I have a term that divides each one of those terms at the same time? In this case, yes, because 4 is a factor of 4, and 4 also happens to be a factor of 64. So I could take out a common factor 4 of x squared. Remember that you divide that term by 4 and that will give you x squared, and then minus 64 divided by 4, that is minus 16. So this is a case I've taken out a common factor, and once I've taken out that common factor, I now check and I see that inside my bracket here I do have a difference of two squares. Difference is a minus. X squared is a perfect square because it has a square, an even number exponent, and 16 is a perfect square because 4 times 4 is 16. In other words, the square root of 16 is 4. So knowing that, I will then say that I can just leave out the 4. I cannot take it away. I'm going to leave the 4, and now remember how we factorize the difference to the squares. We have the sum and the difference of the square root of the two terms. So in other words, the product of the sum and the difference. So x, that's x squared, 4 and 4, that's 16, and that's the difference of the squares. Okay, right, let's have a look at part B. Okay, and in this case what I've got here is I've got again the same case. I'm going to look and see if I can factorize by taking out a common factor. I can take out a minus 8 common factor of x squared minus 1, and I'm just going to go a little quicker now, and again realizing here in this case that I've got a difference of two squares, so I can factorize that further. So I'll keep the minus 8 outside, and then in here I'm going to have the sum and the difference of the two roots, so x plus 1 times x minus 1. And again I just look and I say there's no ways that I can factorize any further, so I found my solution there. Okay. In the third question in this case, what I'm going to do is I'm going to look and say, well, again, question ask, do I have a common factor? Yes, I do. I've got a 3 common factor of x squared minus 81 y squared. Okay? And again, the next question follows and says, well, now I've taken a common factor. Have I finished my factorization? No, because I'm factorizing fully, and I realize that inside the bracket here I've got a binomial, and that x squared is a perfect square because exponent is an even number. 81 is a perfect square because the square root of 81 is 9, and y squared is a perfect square because exponent is an even number. So therefore I can just go on and say, so 3 times, and I'm going to then go and multiply the sum and the difference of the two square roots. So x plus 9y and x minus 9y. Okay, sometimes I've always had the question, does the order matter? It doesn't matter. You could actually say minus and plus. It doesn't really matter. The bottom line is that you have to be able to show that you have factorized by multiplying the sum of the difference of the two square roots of the two terms. So with this I have now factorized expression fully, and there's no ways, there's nothing else I need to do. So that is some examples of factorizing difference of two squares. Alright, so let me now move on and look at, let me just use the same paper here. So what I'm going to do now is I'm going to take a look at how to factorize the, so still remember I'm still factorizing fully. So now I'm going to focus on trinomials. Okay, so let me just take a couple of examples of trinomials and then we'll see how we factorize them. So I'm going to start with, in this case, I've got x squared plus 12x plus 27. Then I'm going to factorize a squared plus 6a minus 27. Then I'm going to look at something like 2x squared minus 4x minus 30. And then I'm going to look at something like 81 minus 18a plus a squared, and I'm going to factorize. Okay, so let me just number them. So a, b, c, and d. Okay, and now I'm going to proceed to factorize these polynomials. So starting with the first trinomial, the first thing that I need to check, and remember that for the purpose of this course, the first thing that I need to know is that the coefficient of the square term has to be 1. And once I've got that, then I know that I can factorize the expression. So how am I going to do that? Well, I'm going to do that by taking the last term and splitting it into a product of two terms in such a way that that product adds up to 12. Once I found a pair of numbers that multiply together is 27 and added together is 12, then I would have had my solution. Now, there are many ways and many theories, and they talk if that one is positive and that one is positive. But what I'm going to do is I'm going to give you a general way, and then as you go along, you will be able to sort of master the skill a little more and be able to do this. So what I'm going to look is I'm going to look at all the pairs of integers in this case that multiply to positive 27. So let me start with the simplest of them all. So that's 1 and 27. So 1 times 27 is 27. But also minus 1 times minus 27 is also 27. I also got that 3, which is the next prime factor of 27, times 9 is 27, but also have that minus 3 minus 9 is 27. Okay? And if I try and know there is no other integers, so I'm going to do with this one. So now what I'm going to do is I'm going, by process of elimination, I'm going to look and see what is the addition of these two terms. So if I added 1 and 27, that's going to give me 28, and what I'm looking for is I'm looking for 12. So 1 plus 27 is 28. That doesn't help me, so I'm going to take that one out. Minus 1 minus 27, that doesn't help me because the answer is going to be negative anyway, and I'm looking for a positive answer. Then I've come to 3 and 9. Now 3 plus 9 is equals to 12. 3 plus 9 is equals to 12. So here I've got a pair of numbers that multiply together is 27 and added together is positive 12. So I'm going to go on and say, now that I've found that I've identified those, I'm going to say, so my two factors are going to be x plus 3 and x plus 9. Now, if you were to multiply those two, and I want you perhaps in your added time to look at this, if you were to multiply that out, you will then end up with that same expression. And this is the idea behind factorizing trinomials. Now I'm going to look at the second example, and the reason why I wanted to leave it pretty similar was because I wanted you to see the difference between what I did before and what I'm wanting to do now. So in this case, I've got the same case. The coefficient of the square term is 1, so I will proceed to factorize it. Remember that we're only going to work with coefficients of 1 in the course that we're currently doing. So in this case, what I'm going to do now is I'm going to go and take and say, well, how do I factorize, or how do I split the minus 27? I'm going to say, well, I could write minus 27 as minus 1 times 27, or I could write it as minus 27 times 1, or I could write it as minus 3 times 9, or I could write it as minus 9 times 3. Okay, so here I've got all the pairs of numbers or integers that multiply together, multiply to minus 27. Now only one of those pairs will satisfy the condition that when I add them, the addition of the two is going to be positive 6. Okay, so let's just start. So minus 1 plus 27 is 26, so I'm not going to take that one, I'm going to ignore it. Minus 27 plus 1 is negative 26, so I'm not going to consider that either. Then minus 3 plus 9 is positive 6. Again, I think I've struck gold, and I'm actually been third time lucky both times. So in this case now, I have now found one where the two numbers that multiply into negative 27, when you add them together, that gives you positive 6. So that means that I found a pair that satisfies my condition. So what I'm going to do then is I'm going to go and say, in this case, and I forgot to put the equal here as well, my two factors are going to be, and remember I always have two factors in this case, because the coefficient of a squared is 1, or the variable is actually squared. That's why we have two factors, so a, and what goes on this side is the two factors that I found of minus 27 that add up to positive 6. So minus 3 over here and plus 9 over here. Now I'm going to make it very clear that this is a very basic way of doing it. There are many fancy terms or fancy ways of doing this out there. I'm not going to delve into those now. You could actually do that once you master the skill. These are the basis of the skill, and this is how we go about finding these pairs of numbers. Okay, all right, so let's have a look at the next example. Now in the next example, I've got one of those expressions. Now what I noticed straight away is that the coefficient of the square term isn't 1. So the first thing that I should be attempting to do now is I'm going to attempt first to try and pull out a common factor. Okay, I need to check if I have a common factor here, and indeed the 2 is a factor of 2, 2 is a factor of negative 4, and 2 is a factor of negative 30. So I could go ahead and say I'm going to take 2 out as a common factor of, and then you divide each term of the polynomial by 2, and that's going to give you x squared minus 2x minus 15. Okay, and again, I've done my first factorization, but because I'm factorizing fully, I still need to check and see if there is no other ways to factorize this further, which there is. Now I've got inside the bracket here, I do have one of those polynomials where the coefficient of the square term is 1. So what I need to do now is I need to check for two integer values such that when I multiply them I get minus 15, and when I add them I get minus 2. Okay, so let's go through the motions. My values here will be minus 1 and 15, because multiplied together that will give you minus 15. But it could also be minus 15 and 1. It could also be 5 or minus 5 and 3. Okay, and it could also be minus 3 and 5. Okay, is there any other pair of integers that multiply to negative 15? Not that I can think of, so I'm going to work with this pair that I've got. And the first thing that I need to ask myself is, I need to go and check and say, well, now let me check which one of those four pairs that I've got add up to negative 2, which is what I'm looking for. So in this case, minus 1 plus 15 is 14, so that doesn't work. I'm looking for minus 2. Minus 15 plus 1 is minus 14, that doesn't work. And then minus 5 plus 3, that is negative 2. Wow, I'm lucky again. I've just got it 3 times, third time lucky. So maybe third time lucky for me does it. Okay, so now I've got a pair of numbers that when I multiply them together, that gives me negative 15. When I add them together, that gives me negative 2. Okay, so in this case, what I'm going to do then is I'm going to say, so 2 times, and then I'm going to open my two brackets. Remember how I factorize? We factorize the trinomials. The variable, so x here and x there, because remember that's why the coefficient of the I want the coefficient of the square term to be 1, and then I'm going to use those two values, so minus 5 here and plus 3 over there. And again I double check that minus 5 times 3 is minus 15, and minus 5 plus 3 is negative 2, so that means that I have factorized the expression completely. Okay, alright, so now I'm going to look at the last one. Now in the last one, you might perhaps look confused because you don't have the square term in the beginning. That isn't a problem. You could factorize the expression as is, but I think that to make life easier and to actually get to some kind of standardization, what I'm going to do here is I'm going to rearrange. I'm not going to change anything. I'm not going to take out a common factor because I realized that the coefficient of the square term here is 1, so I don't need to worry about taking out a common factor or anything like that. So what I'm going to do is I'm going to just rearrange that expression, and what I'm going to do is I'm going to bring the a squared to the beginning and say a squared minus 18a, okay, plus 81. Okay, and what I'm going to do now is I'm going to look for factors of 81 that multiply to 81 and add up to negative 18. Okay, so 81 has 1 as a factor, so I could say 1 times 81, or I could also say minus 1 times minus 81, because both of those pairs multiply to positive 81. But I could also say 3 and 27, or I could say minus 3 and minus 27, because when I multiply those two pairs I also get positive 81. Or I could say 9 times 9, or I could say minus 9 times minus 9. And I think that I've covered all the pairs of integers that multiply to negative 80, to positive 81. Remember, they both have to be positive, or they both have to be negative, because the product is a positive value, and the only way to achieve that is by using a positive value. Now, what I'm going to do is I'm going to go through my method of elimination and say which one of those pairs add up to negative 18. So, is it 1 and 81? No, that's 82. Is it minus 1 and minus 81? Obviously not, that's minus 82. Is it 3 plus 27? No, that is 30. Is it minus 3 minus 27? No, that is minus 30. Okay, is it 9 and 9? No, that is 18. Is it minus 9 and minus 9? Yes, minus 9 is minus 18, whereas minus 9 times minus 9 is positive 81. So I think I just struck gold here, and I say, so my two factors therefore will be a minus 9 and a minus 9, and I double check again that minus 9 times minus 9 is positive 81, minus 9 is negative 18, and that tells me that this is correct. Now, there could be a way in which you could write that even more abbreviated, and because you're multiplying the same factor twice, you could write this as a minus 9 all of it to the power of 2, because you're multiplying the same factor twice. Okay, alright, so we have looked at products, we have looked at factorization. Let's just look then at some applications of the products and factorization. So where do we use this in algebra? Again, remember, this is an abstract concept, so where do we use this in algebra? I'm going to start by looking at how do we simplify algebraic expressions. Okay, so here I've got some cases of algebraic expressions that I need to simplify. Now, a common misconception or maybe common mistake is that pupils actually tend to go and look at this and say, well, I could simplify the x squared and the x squared because it's the same. I could simplify the x and the x. I could simplify the 12 and 14. And that is a gross mistake. You cannot factorize this expression because they are not written as a product of factors. And that's the same thing what you do with numbers. That's the same thing you learned to do with numbers before. You can only simplify a numerical fraction. So let's say, for example, you had something like 36 over let's say 84, for example. Okay, now when you look at these two expressions, the only way that I could simplify that is if I could multiply, or I can find a common factor of both the terms. So sometimes people do it directly. Some other time what they do is, if I write that as a factor, as a product of factors, what do I get? So remember the prime factorization, etc. I'm not going to take you through the whole process, but you could say that 36 is the same as me saying 2 times 2 times 9, times 3 times 3. Okay, 2 times 2 is 4, times 3 is 12, times 3 is 36. Whereas 84 could be factorized as follows. So 2 times 2 times 41, I think. 41 is a prime number, so I couldn't be able to factorize that any further. Okay? No? No, sorry, my apologies. Not 41, that's 21, so it can be factorized further. Let me just get my eraser here. Okay, so you see, that's why sometimes you actually have to do it the proper way, otherwise you might get confused. So when I start here and I say, so 84 divided 2, that's 42, divided by 2, that's 21. So now I'll divide it by 3 and then times 7. So let's double check if I did it correctly. So 2 times 2 is 4, times 3 is 12, times 7 is 84. You see, so now what I've done is I've reduced the 2 to a product of factors. Let me just move this a little bit. I've reduced it to a product of factors, so now I can simplify the factors that are equal. So 2 simplified with a 2, that factor simplified with that factor, these 3 simplifies with that 3, and all I've got here is to say that you could simplify that fraction to be just 3 over 7 because you simplified using prime factor. So similar to that is what we do with the algebraic expression. We have to write this algebraic expression, only that unlike the numbers where the factors are numerical factors, here the factors are also algebraic expressions. So I need to use what I learned before. I need to use my dots, my trinomials, and see how I can factorize those expressions. Okay, so let's give it a try. For the first one in this case, okay, I've got a fraction. What I'm going to do now is I'm going to factorize both the numerator and the denominator. And again, I'm not going to go to the process in such detail. I'm just going to take you through how this goes. So I'm going to factorize that trinomial, and the factorization of that trinomial is x minus 12 and x minus 2. Okay, so x minus 12, x minus 2. Alright, minus 12 times minus 2 is positive 24, minus 12 minus 2 is negative 14. On the other side, I've got that I could factorize that trinomial, and again, I'm not going to go through detail. The coefficient is 1, there is no common factor, so this would be x minus 12 and x plus 1. Okay, minus 12 times 1 is minus 12, minus 12 plus 1 is minus 11. So what I've achieved here is that I have now written my two expressions into the product of factors. I could only simplify factors. I could not simplify single terms when they're written in polynomial form. So what I'm going to do now is I'm going to take and see, do I have any common factors in my numerator and denominator that could be simplified? Yes, I've got an x minus 12 here and an x minus 12 there, so I could simplify those two. And once I've done that, and I check that I cannot simplify any further, what I've got left in my numerator is x minus 2. What I've got left in my denominator is x plus 1. Okay, alright, so let's have a look at the next one. In the next one, again, the same idea. So I need to factorize before I can try and simplify it. So the first thing that I'm going to do here is I'm going to look for a common factor, because I think I do have a common factor in the numerator, and indeed I do. So that would be 2 times x squared minus 16. And I realize immediately that that is further can be simplified as, and remember, I haven't forgotten about the denominator, I'm just working on the numerator alone. So 2, and again, what I have here is a difference of 2 squares, so it's a minus, there's 2 terms, so that will simplify it into the sum and the difference of x and 4, which is the roots of the two values. So x plus 4 times x minus 4. Okay, and I'm done with the numerator now. I've just expressed my numerator in the terms of factors alone. So now I'm going to go to the denominator, and I said, oh wow, look at this. I could take out a 4 common factor, because the only way for me to factorize that, or to get factorize this trinomial, is if the coefficient of x squared is 1. So I'm going to first try and take out a common factor out. That's going to give me inside the bracket is x squared minus 3x, because 12 divided by 4 is 3, and minus 4. Now I realize that what I have inside the bracket is a trinomial, so I'm going to then attempt to factorize that trinomial, and I know that I can. I'm not going to go get into detail. You can go back in the video and find out how to factorize the trinomials more in detail. So I find two factors of minus 4 that add up to negative 3, so those will be x minus 4 and x plus 1. Again, what I have here is that I've been able to write both my expressions as a product of factors, and once I've got that, I can then look and simplify the common factors. Remember, all factors, it has to be all written in multiplication case like it is this. So I could say I've got an x minus 4 here, which I will simplify with this x minus 4 over here, and then I've got a common factor to 2 and 4. So if I divide the 2 and the 4, both of them, by 2, I'm going to have a equation of 1 there, and I'm going to equation of 2 here. So in that case, I can say that all I've got left here in the numerator is 1 times the x plus 4. In other words, it would just be x plus 4 over, and in the denominator I've got 2 times x plus 1, so 2 times x plus 1. I often get asked the question, so should I expand that further? Well, you could, I guess, if you wanted to make it look a little bit more pretty, and you can get to x plus 4 over 2x plus 2, but it's not really necessary to do that, since what you wanted to do was simplify the fraction a little further. Okay, all right, so let's go to the next one. Now in this case what we have is we have a division of two fractions. Now very, very important that when you have a division, that is something that you have to do, and that is that you have to convert. You cannot divide fractions like that. You need to first convert it into a multiplication. How do you convert it into a multiplication? By switching around the other fraction. Normally you would call it, or tend to call it, tip and times. So you're going to tip that, you're going to turn it around, and then change the division sign to a multiplication sign. So the first thing I'm going to do here is I'm not going to do any factorization now. I'm just going to write this as 16p to the power of 4 minus 1, just as it was, over, okay, 4p squared. And I could have gone to factorize it, but I don't think I want to do this at this point in time. Okay, minus 1, and then I'm going to change the division sign to a multiplication sign, and I'm going to turn the other side fraction around. So in other words, my numerator is now going to be 4p squared plus 1, and my denominator is going to be 1. Okay, now that I've got that, I can then proceed to try and factorize all my expressions. Okay, so what I'm going to do here is I'm going to go on and say, so in my numerator what I have is, I've got, when I look at this, there is no common factor, so my first fraction doesn't have a common factor in the numerator. The only way that could be factorized if it is a difference of two squares. Let me check, it is a difference. That is a perfect square, so 16 is a perfect square, and p has an even number exponent, and then minus 1, which is a perfect square. So I could factorize that into 4p squared plus 1 times 4p squared minus 1. Okay, and then I notice that that is also a difference to the square, so I could go on and factorize that further. However, and I'm just going to move this a little bit this way, however, I notice that the denominator in my fraction is also 4p squared minus 1. Okay, and I could put a bracket around because I could consider it as a full term, and I wouldn't need to factorize that further if I know that I could simplify that together with that. Now if you did not realize that, and this is the scenario that I'm going to take, then you could go on and factorize that as a difference of two squares, and then you will have to factorize that as a difference of two squares, and eventually you're going to get to simplifying both of them. So I'm just going to go ahead and do the simplification now. I'm not going to worry about this anymore. So then when I look at there, I tried to factorize, but this is not a difference of two squares, it's actually a sum of two squares. That is a perfect square. Yes, that is a perfect square, but this is the sum of two squares, not a difference of two squares. I don't know how to factorize that for now, so I can just go on and say, so I can factorize this by simply leaving it as is, so 4p squared plus 1 over 1. And now that I've looked at that, I realize that I've been able to simplify all the equal factors, and all I've got left in the numerator is 4p squared plus 1 times 4p squared plus 1. So I could write that as 4p squared plus 1, all of it to the power of 2, because I'm multiplying the same factor twice, over 1, or simply leave it like that, because remember that your denominator 1 doesn't really make a difference. Okay, all right. To the last question, and in this case, again, I've got a fraction that I want to simplify. This is not a division or anything like that. It's just simply a fraction that I need to simplify. So I'm going to start with my numerator, and when I look at my numerator here, I notice that in my numerator I could take out a common factor. 8 is a factor of 8, and so is a factor of 32, and here I've got x to the power of 6 and I've got x squared here, so I could take out as a common factor 8x squared, and then inside my brackets I'm going to have 8x squared, or 8x to the power of 6 divided by 8x squared. That's going to give me x to the power of 4. Okay, and in this case now 32x squared divided by 8x squared, that is equals to minus 4. Okay, now I'm going to go to my denominator, and again, and I notice that in my denominator I've got also a common factor, because 12 is a factor of 12 and 24, and x to the power of 4 is a factor of 6, or x to the power of 6 and x to the power of 4. So I'm going to take 12x to the power of 4 out as a common factor of, and inside the brackets I'm going to have x to the power of 2 plus 1, because you notice that the second, sorry, plus 2, my apologies, not plus 1, plus 2, because 24 divided by 12 is 2, so plus 2 over here. Okay, now in the numerator, I further know that after I've factorized here, I've got a difference of 2 squares here. It is a difference. There is an even number exponent. There is a perfect square. So I could go in and say, I'm going to simplify. I'm going to keep the ax squared over here. Then I'm going to say this is a product of the sum and the difference of the square root. So x to the power of 2, which is the square root of x to the power of 4, plus 2, and x to the power of 2 minus 2. In the denominator, then I've got the 12x to the power of 4 times x squared plus 2. And now that I've written everything as factors, you can see there's no plus that is not that is outside the bracket, which means that I've got all my factors here. I can then proceed to factorize further or to simplify further. So what am I going to simplify? I'm going to simplify x squared with x squared, and I'm going to simplify the 8 and the 12. They're both divisible by 4, so 8 divided by 4 is 2, 12 divided by 4 is 3, and here I'm going to simplify the x squared with the x to the power of 4, where x squared divided by x squared is 1, and x to the power of 4 divided by x squared is x squared. So all I've got left here is I'm going to say that in my numerator, all I've got left is 2 times, because that went, so is x squared minus 2 over, and in my denominator I've got 3. Remember that I've got the x squared that I was left with here, so 3 times x squared, and there's nothing else because I simplify that. So I should have actually written this a little bit more in the middle to make it look a little prettier. So that would be 3x squared, and I double check that there's nothing. Now you cannot simplify those two. Remember that this number 1 is inside the bracket, so you could only simplify the whole term, not part of it. Okay, all right, so there's an example of simplifying fractions. Now everything that we've done here goes a long way into solving equations. So the next part that I'm going to look at, and I think perhaps this will be the last part for this afternoon, is I'm going to look at solving equations. So I'm going to look at solving, and I'm going to put two types of equations: linear equations okay, and simple quadratic equations. So let me start with the linear equation. Now a linear equation is identifiable because when you simplify your expression, you end up with an exponent for the equation that is 1. So let me give you an example of what a linear equation looks like. A linear equation in the simplest form perhaps that you will see looks something like this: 4x plus 6 equals 18. And remember, in class what I've said is that you look at a linear equation and you need to think of it as a balanced scale. What happens to a balanced scale? A balanced scale is always balanced, and if you remove something from the one side of the balance, you need to remove it from the other side so that you keep the balance between the two. If you don't, then you're going to fall in the trap that your equation is not balanced, and therefore you won't be able to find the correct. So the whole idea here is I need to find a value of x that when multiplied by 4 and added 6 to it, it gives me 18. Okay, so there are various ways, there's numerous ways of doing this. Say whatever I take away from here, I take away from there, or simply they say, and there's some teachers that say, well, the only rule that I'm going to keep in mind here is that if I move something over the equal sign, I change the sign of it. So there are many theories, and you will use the one that is more convenient for you. So in my case, because I want to balance the equation, what I'm going to start by doing is I'm going to start by taking the equation, and I'm going to find the value. In order to find the value of x, I'm going to subtract 6 from this side, which means that I'm going to subtract 6 from the other side as well. If I subtract 6 from both sides of the equation, on that side, if I've taken away the 6, I'm going to be left with 4x equals, and 18 minus 6, that is equals to 12. So that means that 4 times a number is equals to 12. You could actually by inspection say, so 4 times what number is 12 is 3, or you could simply say, what I'm going to do now is, because the coefficient of x is not 1, I'm going to divide by what the coefficient is, whichever one that coefficient is. In this case is 4, but I'm going to do the same on the other side of the equation. Remember that I need to keep that balance. So when I have 4 divided by 4, that's 1. So that's going to give me x equals, and 12 divided by 4 is equals to 3. So that is potentially the solution to my equation. What I'm going to do now is I'm going to check that it works. So that means that if I go here and I put 3 there, 4 times 3, that is 12, and 12 plus 6 is equals to 18. So if I substitute the 3 in the value of the equation, that expression will have the value of 18. And that's what solving an equation is all about. Now, a variation to solving an equation is to solving an equation when I have brackets involved. So that's the second example that I'm going to look at. So when I look at this example over here, I've got that I'm going to, here an example is 3 times x minus 2 equals to 2 times x minus 3. Okay, and the idea is I need to find what value of x will actually make that true. Now, in order for me to do that, what I need to do is I need to try and isolate the x on the one side so that I can then balance the x with whatever value there is. So what am I going to do first? I'm going to use a little bit of distributive law in order to solve, or in order to remove the bracket. So I'm going to multiply the 3 times the x, the 3 times the minus 2, so I've got 3x minus 6 equals, and here I'm going to do the same, so I'm going to multiply the 2 by the x, the 2 by the minus 3, and that's going to give me 2x minus 6 again. Okay, now once I do that, I realize that on this side of the scale I've got two values that are exactly the same. You see, you've got a minus 6 here and you've got a minus 6 there. So if I was to take away those two minus 6's, okay, I could actually remove them because they are basically the same thing on either side of my balance scale. So I've got I could simplify them. Alright, so in this case now what I have is that I've got the 3x is equals to 2x. Now there is only one value that will satisfy that equation, but the right way to do it will be, I'm going to then, because I need to find what is the value of 1x, I'm going to then subtract 2x from each side of my equation. So I'm going to subtract 2x from here, and I'm going to subtract 2x from that side. Now 3x minus 2x, that is equals to x, and 2x minus 2x is equals to 0. So the value of x is 0 in this case. Question is that possible? Let's have a look. So if I substitute the 0 over here, 0 minus 2 is negative 2, and negative 2 times 3 is negative 6. So that side has a value of negative 6 when x is equals to 0. And on this side, 0 minus 3 is negative 3, and negative 3 times 2 is negative 6 as well. So that side of the equation has a value of negative 6. So when x is equals to 0, that equation is balanced. And I found the value that balances the equation. And that's the whole idea with solving linear equations. Okay, so let's have a look at another couple of linear equations, and I'm just going to try and increase the level of difficulty a little bit more. So, okay, now sometimes the equation looks a little bit more ominous than it is, in that I get some misguidance or some decoys, let's put it that way. So let's say you have an equation that looks something like this. You have let's say (3x), so this is example D, and you're solving the equation, and your equation looks like this: is 3x times x minus 1 minus x times 3x minus 1 equals x minus 6. Okay, so in this case I'm going to operate like I normally do. So I'm going to first use distributive law to eliminate my brackets, and when I do that, I'm going to end up with the following: 3x times x, that is 3x squared, 3x times minus 1, that's minus 3x, minus x times 3x, that's minus 3x squared, and minus x times minus 1, that is positive x, equals, and then on that side I've got the x minus 6. Okay, now with that in hand, what I can do here now is remember that my point is always to group all the x's on the one side. Now, on this side of the equation, everybody's x. On that side of the equation, I've got only one x, and there's no numbers here. So this is actually going to be a case of me saying, so I'm going to keep 3x squared minus 3x squared plus x, and I'm going to bring this x from the other side as minus x equals to negative 6, and that's all that's left on the other side. Now I'm going to simplify here. Now, like terms that I've got 3x squared minus 3x squared. Because they are subtracting each other, you can basically say they simplified, or the answer is 0. And then you're going to take the other values, minus 3x plus x minus x, and that's going to give you minus 3x equals to minus 6. And remember that because I need to find the value of a single x, not a value of minus 3x's, I'm going to divide both sides by minus 3, and when I do that, that gives me that the value of x is positive 2. Okay, which means that if I were to take this positive 2 and I were to put it in the body of my equation, that side is going to have the same value as the other side, and that's the whole idea behind solving equations. Now, equations sometimes may have fractions, and in that case the solution is not very different. It's just the way we go about solving the equation that changes a little bit. So when an equation has fractions, and I'm going to give you two examples of equation with fractions. Let's say the one equation looks like this. Let's say example A, and that would be something like x over 4 minus 2x over 3 is equals to 5. Now, because I've got three different fractions here, I've got a fraction with denominator 4, I've got a fraction with denominator 3, I've got a fraction with denominator 1, I can't really seem to find a solution to that unless all my denominators are equal. Just like you do when you're adding fractions, you're always looking for equal denominators so that you can then promote the addition or subtraction of the fraction. In an equation, it's exactly the same. So what do I need to do? I need to find a common denominator, but not just any common denominator. I would like to find the lowest common denominator in order to solve the equation. So in this case, when I look at my denominators, and I'm going to, for the sake of the demonstration, I'm going to make a 5 with denominator 1. When I look at 4, 3 and 1, where is my lowest common multiple of 4, 3 and 1? The lowest common multiple of 4, 3 and 1, which is my lowest common denominator, is 12, because 12 is a multiple of 4, 12 is a multiple of 3, and 12 obviously is a multiple of 1. So with that in mind, I'm going to go on now and I'm going to say, so for me to solve the equation, I need all my denominators to be 12. Okay, so I need all my denominators to be 12. Now, in order to achieve that, what I'm going to do is I'm going to now go and say, so how did I achieve to get a denominator 12 from 4? I had to multiply by 3. So what I've done to the denominator, I will have to do to the numerator. So my numerator then will be 3 times x. In the same way here, to get from 3 to 12, I had to multiply by 4. That means that I will have to multiply my numerator also by 4. And 2x times 4, that will be 8x. On the other side here, I've got 1, and I transform it into 12. The way to get from 1 to 12 was multiplying both sides by, or multiplying by 12 here. I need to do that to the numerator, so my equivalent fraction is going to be 60 over 12, because 12 times 5 is 60. Now that I've got all my denominators equal, I can go on and say, well, since all my denominators are equal, my solution never doesn't lie anymore in the denominator, it lies in the numerator. So I'm going to proceed to eliminate or to get rid of the denominator. Don't need to talk about the denominator anymore. I can go on and say that 3x minus 8x is equals to 60. Okay, and I am so lucky that in this case I don't need to be switching anything around, because I've got all the x's on the one side, all the numbers on the other side, or the one number on the other side. So I can go on and say, so 3x minus 8x, that is minus 5x, so proceeding to simplify it, and that is equals to 60. So if minus 5 has a value of 60, that means that each one of the x's has a value of negative 12, because 60 divided by minus 5 is equals to negative 12. Okay, so there I found the solution. You can now go here and see if it works. So if you had on this side minus 12 divided by 4, that will give you minus 3. and then minus, and on that side 2 times minus 12, that is minus 24, and minus 24 divided by 3, that would have been minus 8 with a minus, so that would have been minus 8 over here. Okay, so minus 3 minus minus 8, that is equals to 5. So on this side is 5. Okay, and you can see that then on that side I also have a 5. So the value of the left hand side and the value of the right hand side are equal, therefore x equals minus 12 is good for me. Okay, now what variations from this type of equation do we have that can actually come? That is the case that instead of having numbers in the denominator, I have variables in the denominator. So here is an example of that. So let's say my equation looks something like this. I've got an equation that looks like this. 3 over x minus 1 over x is equals to 2 over x, 2 over x plus 5 over 2. Okay, let me try and draw the line here so that you know, okay, where I'm. Okay, so in this case, same thing. I'm looking at my equation and I'll see that my equation has distinct denominators. So in order to solve that equation, what I need to do is I need to solve or find an LCD so that I can convert all my denominators to the same. Now, how many different types of factors do I have in my denominator? I've got 2. I've got an x, which appears in another 2 denominators, and I've got a 2 that appears only in one denominator. But in order for me to get an LCD, that LCD will have to be 2 and x, so in a combination of the 2. Now, with that in mind, I will then proceed to amplify all my fractions, okay, to have a common denominator 2x. So 2x, 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 2x. Okay, when I do that, I say now I ask myself the question, how did I get from x to 2x? I multiply by 2. Okay, and when I multiply by 2 the denominator, I also have to do it to the numerator, and 3 times 2 is 6. From x to 2x here, again multiplying by 2, so my numerator, which is 1, is going to be multiplied by 2, and that's going to give me 2. Equals. On that side, again, x to 2x multiplied by 2, so that means my numerator is going to have to be 4. And last but not least, I need to get from 2 to 2x. The only way to do that is by multiplying both sides by x, and that's what I'm going to do with the numerator. So I'm going to write it as 5x divided by 2x. Okay, now that all my denominators, remember my bottom line was to achieve that all the denominators were the same. Once I've got that, I can say that my solution doesn't lie any longer in the denominator, it lies in the numerator, and I can then solve my equation for x in this form. So 6 minus 2 equals 4 plus 5. So in this case, what I'm going to do is I'm going to promote the 4 to the other side, so that will be 6 that was here minus 2 that is here minus 4 that comes from the other side equals to 5 times x, and then I work it out. So 6 minus 2 is minus 4, and 6 minus 2 is 4, and 4 minus 4 is 0. So I've got that 0 equals to 5x, and there's obviously only one number that you multiply by 5 and give you 0, and that is x equals to 0. Okay, if you didn't want to do it that way, you're welcome to go and multiply both sides by 5, and 0 divided by 5 will give you 0. Okay, so that is an example where the equation actually has an x in the denominator. Now, the last example that we're going to look at today is we're going to look at some examples of simple quadratic equations. Okay, and in this case we're going to look, for the interest of this course, we're only going to look at one thing, and that is when my equation is written in the form of factors. Okay, so when my equation is written in the form of factors, let's say for example I'm wanting to solve the equation 2, let's say x minus 1 times x plus 2 equals to 0. Okay, and then I'm going to try and solve the equation 2x minus 9 times 4 minus 3x equals to 0. And then last but not least, I'm going to go and solve an equation that has a few more than one term. It's going to look something like this. It's going to be 2x, so let me just say c, will be 2x times x minus 4 times 3x plus 7 equals to 0. And let's see how we go. Now, again, the bottom line here is, for the sake of the course that we're busy working with, the bottom line here is that what I'm looking, and the way you need to look at this is, I've got a product of two factors, and that product happens to be 0. There's only one way that this is going to happen, and that is if each one of those factors, or both of them, are equals to 0. So what would be the possible solutions here? Would be the values of x that make that factor 0, or the values of x that make that factor 0. Okay, so what value can I substitute the x by to make that factor 0? So if x had a value of 1, 1 minus 1 is going to be 0. And no matter what value that is, the product of the two is going to be 0. So one possible solution here is x equals 1. The other possible solution is when I take that and I say, so I can say x equals to 1, or I'm going to look now and say what value of x make that 0. If x had a value of negative 2, minus 2 plus 2 is going to be equals to 0, and therefore doesn't matter what the value of that, when you multiply by 0, your answer is going to be 0. So there is two possible solutions for that equation. Those are x equals 1 or x equals negative 2. Okay? Now, I found the two solutions. Remember, if you substitute the 1 here, that becomes 0, and doesn't matter what the value of that is, the product will be 0. Same thing here. So when I look at it, I've got a product of two factors equals to 0. So all I need to do is I need to say, so what values of x will make that 0? Now this is a little bit more complicated, so I'm going to write it out and I say, so let me find out how can I make that equals to 0. I'm going to solve it like I solve a normal equation. So I'm going to move the 9 across to x equals 9, and I'm going to now divide by 2, so 9 equals to, or x equals to 9 over 2. And there is the one solution. So x could be 9 over 2, or the other solution will be when 4 minus 3x is equals to 0. Again, not a simple solution, okay, or not as an integer number solution. So I'm going to then move the 4 across to the other side. So that's going to give me minus 3x is equals to negative 4, because I move it across to the other side. And now dividing both sides by negative 3, that's going to give me that x is equals to negative 4 over negative 3, which in other words is 4 over 3. And there is the two solutions. So the one solution is x equals 9 over 2. The other solution is x equals 4 over 3. Okay. All right. Now in this case, the difference is that instead of 2, like I've seen before, I've got 3 terms. But the principle is exactly the same. Because this is a product, whenever one of each product, these factors is 0, or all of them are 0, then you have a product of 0. So all I need is one of those 3 factors to be 0, and that will make the equation true. Therefore, I will have 3 possible values, because if x is equals to 0, that will make 0 that expression, and that means that 0 times whatever that is will give me 0. If x is equals to 4, 4 minus 4 is 0, and if that term is 0, it doesn't matter what those two terms are, the product is going to be 0. Or when x is equals to, and I'm going to go out on a limb here and write it in one shot, minus 7 over 3, so the opposite of that divided by that. If you were to substitute by minus 7 over 3, minus 7 over 3 times 3, that's going to give you minus 7, and minus 7 plus 7 is going to give you 0. It doesn't matter what the value of these two factors are, the product by 0 will give you 0. So therefore, these are your 3 solutions in this case. Okay. Now, I hope that with the lesson today, I've gone a little bit further than I expected. I was expecting to just be under about 45 minutes as it is in a normal lesson, but I went a little bit over. But I hope that with this, it actually has cleared out very well how we work with products, how we do a little bit of factorization, how we use the factorization on fractions, and also how we solve simple equations. Okay? Once we've covered a little bit more work in class, we will then be able to go a little bit deeper into factorization and the use of factorization. We're also going to start solving equations that are not as simple, or quadratic equations that are not as simple as the one that you see here, a little bit more complicated. We will have to go through factorization, etc. I hope that you like this. I hope that it teaches you something, and yeah, good luck with the work in future, and we will see you next time. Bye bye.